Okay, I'm coming. All right, so when we talk about the mole, if we want to talk about the equivalent of a mole in mass, you have to be able to convert. You have to be able to convert to mole. That's one thing we're going to learn how to do. If you want to be able to convert to number of particles, so if I give you half a mole, how many particles is that? A mole has how many particles in it? Right, 6.02 times 10 to the 23rd particles. So half a mole would be,
Over 2.
huh?
Over 2.
Divided by 2, whatever that is divided by 2. So about 3.01 times 10 to the 23rd. Just cut that number in half. So if I ever want you to calculate that, I'm going to give you a mole and then say convert with dimensional analysis. Remember your units where you cross out your units? We're going to do that a bit today. So the first one, Avogadro's constant. Pause. Okay, so Avogadro's constant is 6.022 times 10 to the 23rd, and I do this a lot, 0.022, because that's the extra decimal. So if you want to keep it as 0.02, your answers will be really similar, so no big deal. So this is number of particles equal to 1 mole. So remember, when anything's equal to each other, we can actually write it as a fraction. That's what we did in dimensional analysis. So anytime you can, trying to cancel out units, you're going to write 1 mole over 6.022 times 10 to the 23rd. Particles, it might be atoms, it might be formula units, whatever. And so if I had, let's say I had given you 7 particles, really random number, but 7 particles, those particles, that whatever that unit is, will cancel with this particle unit, and that will allow you to, if you calculate correctly, will allow you to convert to number of moles that 7 particles make up, which is going to be something crazy low, really low number. Whenever I want you to convert between moles and mass, it's called molar mass. It kind of makes sense, right? Moles, mass. So if I have 1 mole of something, that's something. Give me an element, any element. Oxygen. I'm going to just put O. It's not diatomic oxygen. Huh? I don't have it. Okay, yeah, I do. Okay, here. So, I have oxygen. Look on the periodic table for oxygen. Give your periodic tables out. All right, grab that. Look at the molar mass of oxygen. 16.00 grams. So that's all you're doing is you're looking at the mass of the element, and if I ask for 1 mole of that, it's equal to the mass of the element. But if I give you something a little bit more complex, let's say diatomic oxygen. 1 mole of diatomic oxygen, how many atoms are there? 2 atoms of oxygen within 1 molecule of oxygen. So what are we going to do to the mass? Double it. So what's the molar mass of this? 32 grams per mole is how we write it. So what this means is I have 32 grams of oxygen, O2, per 1 mole of oxygen, O2. So this is how we write it as a fraction. You can do that with anything. You can do that with glucose, C6H12O6. You just got to add them all up. Last bit here is molar mass. Molar volume of a gas. This one has another special conversion. 1 mole of any gas is equal to 22.4 liters. So if I had a gas is spread out really far apart, right? So if I had 6.022 times 10 to the 23rd molecules of gas, it's going to spread out so far, it's going to take up 22 liters. 22 liters is quite large. You know how big a liter is? How big is a 2 liter? 2 liters about this big? Times that by 11. I don't know, like this big. So 1 mole of gas takes up that much space. So that's kind of a lot for a gas, for 1 mole of it too. So we're going to be converting with these conversion factors today. So what you need to know is, maybe highlight or star it. You need to know that if you're converting between moles and particles, you have to use that conversion. If you're converting between mass and moles, you have to use the conversion of molar mass. It's just this number is going to change based on what the heck we're talking about here. It's going to change every time. This number never changes. It's always 6.022 times 10 to the 23rd. If we're going between volume and moles, and you always use this constant, which we always write as like 22.4 liters per mole, or or vice versa. I mean, we can flip things upside down depending on what units we need to cancel. That number never changes either. So the only one that you have to ever calculate is the molar mass one, and we've already done it maybe 2 or 3 times in a last unit, so we'll do it a bit more today. Okay, so this is I think the first part of the guided notes, if I'm thinking right. The SI unit for substance, 1 mole of that. Definition, mole allows us to convert between mole and particles mainly. Okay, so I told you some of this. The top left-hand side, the mass, oh no it's not, I lied to you. Well, that's almost there, those are the problems mainly. So if we're going between particles, there's 3 types of particles. They were in your reading guide. First one, atoms. Next one, molecule, and I just do MOLE apostrophe C to say molecules. It looks like mole, but it's got C on it, so that's molecules. And formula units. Okay, and this is the information for that. We already reviewed this. If you want to write it down again, you can. But these are called the representative particles. The representative particles have 3 variations: atoms, molecules, and formula units. And then we went through this just a minute ago with Madison's question. Elements, all elements contain atoms. So like if I have a bunch of copper, I might have 10 million atoms of copper in that mass, whatever it is. Compounds, like covalently bound compounds, are all called molecules, and all ionically bound compounds are called formula units. Just a quick reminder, we went over this. Oh, how long ago? I can't remember. So I'll give you a second. You're looking at that. What's the gas constant per molar volume? 22.4. Okay, cool. You can say it and remember it. You're in good shape. So the one important point on this one is, yes, you do have to write down molecules for anything diatomic, which is your big 7, and hydrogen, because they are also molecules. So like chlorine gas or hydrogen gas, and so on. All right, we're going to use these a lot. Just the words, remembering what they mean. We can get very far. That's so good. Okay, oh, this is a big picture to show you the same things, okay? So I've got a monatomic gas like neon. Is that diatomic or monatomic? Monatomic is from the picture, right? Diatomic is a molecule, it's got 2 molecules. This is, don't look at the formula, ammonium dichromate, right on your paper. Ammonium dichromate. Don't look. What is it? Go for it, don't look up there. Ammonium dichromate. CR2O7. What did I miss? There's a 2. See that 2 over here? Crisscrosses down here, right? So I gotta put parentheses around my NH4, and there's a 2 right there. Big, huge compound. So is that ionic, covalent, or what? It's definitely ionic, because I had to crisscross ionic charges. So then when I look at the molecule, or at the formula unit, it's big. It's connected to, it's a huge formula unit or thing. But I can actually decompose it. I can say I have 1 mole of this. I make 1 mole of this, 1 mole of this, and 4 moles of this. Guess where these numbers are coming from this balanced chemical equation? This 1 of these, 1 of these, 1 of these, and 4 of these. Take a guess. It's a balanced chemical equation. It's just in picture form. The number I have of them, which is, how do I show that? Coefficient, right. So those things are coefficients. These actually, when I say I have a mole of these, it's just going to say I need 1 of these, 1 of these, 1 of these, 1 of these, and 4 of these. And that's, we're just going to call them moles from now on versus our coefficients. So we're going to start using mole ratios based on the balanced chemical equation. And then you can see a couple more pictures of mixtures and compounds. We went over that stuff in like Unit 1. So we're good with that. Okay, this is just the definition of molar mass. I do not recommend writing all this down. Anytime you see molar mass, a lot of times we've been saying AMU or atomic mass units, but now we're going to start saying grams per mole to be specific. So atomic mass from the periodic table, we're going to look at the PTOE to get the grams per mole. We're not going to call it AMUs anymore, just because that's how, when we do lab work, we can't measure in AMUs. We can only measure in grams, so we just need something we can work with hands-on. And this just happens to be the definition. You guys defined this back in chapter 6 or something like that. We compare everything to the carbon atom. So if carbon smaller mass is 12.01, that should be equal to 12.01 AMUs and 12.01 grams. So it's just a bit more of the textbook talk, but I don't talk in textbook talk so much, so I'm skipping this part right here. Just so you know, you look on PTOE. All right, so we just went through that. Oh, the one thing I didn't show you was standard temperature to 25 degrees C is standard temperature, which is what in Kelvin? We talked about Kelvin way back. At 273 is equal to 0 degrees Celsius. So what's 25 degrees Celsius? What's 25 degrees Celsius in Kelvin? 298 Kelvin. Okay, so anytime we're talking about molar volume, we're talking about standard temperature and pressure. Standard temperature is 298 Kelvin or 25 degrees C. Usually we use Kelvin, we see that a lot. And then 1 atmosphere pressure. Pressure equals 1 ATM or atmosphere. Those are just things that will probably be told to you in the problem in order for you to actually use this molar volume conversion that we're going to use. Alright, we're going to do our conversions. Yeah. You'll see Kelvin a lot more, so start using it, but it's equal. All you're doing is adding whatever the degree Celsius is to 273 to get your Kelvin value. We're going to start using Kelvin a lot more, so if you can start that now, it would be good. And then, oh, I did skip my one thing I wanted to do on molar mass because we have to convert here. Everybody's a periodic table out, right? You have a calculator. If you have a phone with a calculator, if I see you on anything else, I just take it, but just try to stay with me here. Alright, let's go back here. Alright, this is the first part of your notes. I was just going past it. So look at sulfur. What's the molar mass of sulfur? Huh? 32.07 what? Grams per mole, right? Molar mass is, you always write the units grams per mole or 1 mole if you want to. How many atoms are in 55.8 grams of iron? Look at iron. What's the mass of iron? 55.8. So if you have 55.8 grams of iron, how many particles should that be representing? So why I'm skipping it, I'm hoping you can connect your dots. If I tell you have 55.8 grams of iron, what should that equal? 1 mole. I always said it, thank you. Because just like I just showed you here, 1 mole of sulfur equals whatever the grammage it says on the periodic table of sulfur. I'm having you go backwards now. I give you the grams, which is exactly what it says on there. That should equal 1 mole of iron. Well, how many particles are in a mole? Yes, so Avogadro's number. So how many atoms is this representing then? 6.022 times 10 to the 23rd atoms. So in your head, you said, okay, that equals 1 mole, and if that equals 1 mole, then that equals that many atoms. The mole connects everything. It's a stepping stone to pretty much any unit in chemistry. So we use it a lot, and you actually can do that part in your head because I told you that whatever the periodic table says in grams, that equals 1 mole of that particular substance. But everything's different, something's way more. Okay, so if I wanted 6.022 times 10 to the 23rd atoms of carbon, what mass of carbon would I need? All right, how do you know that? That's the mass of carbon. And so that equals 12.01 grams is equal to 1 mole of carbon. Therefore, that's going to equal Avogadro's number of carbon. All right. Okay, good. Sorry, I had this feeling that I wasn't recording, but I am good. All right, let's actually do these now. These are on your notes. They should be. It's doing this weird thing, so I'm going to close or click this out. Okay. So we'll go through some molar mass actually first, and then we'll go through those like class examples. So the molar mass, the first one says water, right? All right, so we have new blue marker, okay? Water, which contains 3 atoms, 2 H's and 1 O, right? So 2 times the mass of hydrogen, what is it? 1.008 grams plus 16 for water for H. So we did 2 of the H's and 1 of the O's. So that give me an estimate. 18.01, right? So this is 2, essentially. That's 16. So 2 plus 16 is 18. You can add up on your calculator. That's fine. You can practice your molar mass in your head though. That's actually water's molar mass, 18.01 grams per mole. Next one, sodium chloride, NaCl. Na weighs 22.99 plus chlorine, 35.45 grams. So, doing your calculator or your head, tell me. I'll just write it down someplace. 58.45. Lovely, people. Lovely. 58.45 what though? Units. Grams per mole. And you know I'm not writing a 1 in front of this mole, but this is 1 and 1. Yeah? It might be from this right here. Some people, it depends on what period table you're looking at. They all kind of round it just slightly differently, but if you put 23 right there, it would be 58.44. That usually, like the last one, I have a lot of these memorized, so I actually just calculate as best I can in my head. As long as we're close, we're good, okay? So, next one, let's do one more. Let's do the hard one. What's the last name? The name of that last one? Magnesium nitrate. Good job. Okay, so magnesium nitrate, Mg, parentheses, NO3 is 2. We got a little bit more complicated here. How many magnesiums? No. There's a 1 right there. Where did that 1 come from? Nitrate's charge, right? NO3, 1 minus. So I've got magnesium plus how many nitrogens? 2. This 2 does distribute in here and in here. Okay, cool. So how many nitrogens? 2. And how many oxygens? 6. So I like to write it like that so I don't mess up. But that's just my preference, and if you get good at it, you can do what you gotta do. So magnesium weighs 24.31. Nitrogen each weighs 14.00. And 6 oxygens times 16 each gives me some big number. I got this for you. What'd you get? 148 or 128? 148. Okay, 148 looks good. 148, I can't actually read if that's a 2 or a 4. Okay, I believe you. So all you're doing in your calculator is saying 24.31 plus 28, or 2 times 14, plus 98, or 90, yeah, I think it's 98. So it should be approximately that. Molar mass is just adding. Cool? Can we move on to another example? Somebody, if you just double check that, usually I have multiple people double check. Alrighty, so we're going to use molar mass as we go through these problems, so we'll do this a little bit more. These are the ones that I want to go through. And my chemistry teacher, when I was your age, taught me how to do the known and unknown method, and it helped me pretty much the rest of my life in chemistry and science in general, math, everything. So I would like for us to try to do this way because it's really helpful. It makes you have to actually do less work in the end. So I'm trying to give you a helpful way. So when you're looking at the question, usually you won't be given something like this simple, like, okay, 2.80 times 10 to the 24th atoms of silicons to moles, because this tells you exactly what I want you to do. It might be in a word problem. It might say, Miss Enlow got some silicon from a factory, and she counted for blah, 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 and just all this stuff. So when you're reading, always underline your known and put a question mark by your unknown. That's the simplest way of doing it. So you always remember what unit you need in the very end, and that way you don't have to go back and double check. So here's my known. I start with my known. This is my starting point. 28 or 2.80 times 10 to the 24th atoms of silicon. And I need to get to moles, right? Can I go directly from atoms to moles? Do I have a conversion factor for that? What's the very first slide notes you just took? Huh? Right, so I can use Avogadro's. Avogadro's number allows me to go between particles, which an atom is a particle, and moles. So what unit has to go on top? 1 mole has to go on top. What unit has to go on bottom? Right. Atoms have to go on bottom, and the number that is associated with atoms is 6.022 times 10 to the 23rd. Atoms of silicon. That allows me to then say this atoms cancels with this atom, and we are left with moles of silicon. And I see if this is my calculator correctly. If you have a graphing calculator, all you gotta do is put parentheses around here, or scientific calculator, whatever it's called, around the numerator there, and then you can multiply by 1 over parentheses Avogadro's number. And when you get that, let me know. So I just want you to practice a couple of them so that you're not stuck later on. Any takers? 4.65 moles. Good. And the reason that works is because this is 10 to the 24th, that's 10 to the 23rd, so your numbers are going to be about 1 decimal off, so that's how you get your full integer there. Okay, next one. Yes, thank you. 0.32 moles of potassium to grams. So known 0.32 moles, and that's what I start with. What's the symbol for potassium? Okay. Okay. And then there's grams, that's what I'm looking for. So what do I need here? What's the only way to go between moles and grams? Now Avogadro's, look on your first page again. Molar mass, right? So moles and mass, that's the only way I can get between them. So where do I need to then go look? Potassium's atomic mass, right. So I'm going to go to the PTOE for that. 39.1. Okay. 1 mole of potassium, 10 years in, decade of science. Okay. 1 mole of potassium weighs 39.1 grams of potassium. Moles cancel, leaving us with grams. Great. 0.32 times 39.1. What'd you get? Okay, so 12.5 grams of potassium. Sig figs. 2 sig figs because of these 2 sig figs that are limiting me. So round. 13 grams of potassium. Awesome. Sig figs love you guys. They miss you. Okay. Next. 1.14 moles of sulfur. Oh, what's the name of that? No, that's only if it's an ion. This is a molecule. Use your prefixes. Sulfur trioxide. Okay, now I'm going to atoms of oxygen. This is not same. So far it's been same. Now we got to get inside the molecule. So let's break it down here. So, here's my known. 1.14 moles of sulfur trioxide. Question, atoms of oxygen. Sometimes I like to write it like this because this reminds me that I just want simple oxygen, not O2, not diatomic, just O. So atoms of oxygen is what I'm going for. All right, so I need to dissect this. I need to get this down farther to the microscale surface of the molecule. There's a couple ways to do this problem though. I'll show you the way I like to do it. These things, these numbers are telling me how many atoms are in sulfur trioxide. So if I have, let me draw this baby out here. I'm just going to draw it like this. Sulfur trioxide. There's a lone pair there someplace too. But how many atoms of oxygen of O are in 1 mole of sulfur trioxide? Or sorry, not 1 mole, 1 molecule. Right, so this now is a conversion factor. I see that there are 3 atoms of O in 1 molecule of SO3. Does that picture make sense? All right, so what do you think I need to get out of here so I can use as conversion factors? I need to get out of moles so I can go to what? Not atoms yet. Molecules. I need to start with sulfur trioxide first before I can finally get down to the nitty gritty of oxygen. So here I'm going to say, okay, I know that a mole contains how many molecules of SO3? I want to go to molecules. Nope. All right, because that's a particle, right? Molecules is one of your 3 particles. So look at that first page of your notes as much as you can so you can ingrain that in your brain there. 1 mole of sulfur trioxide, so I put moles in bottom because they have to cancel, is equal to 6.022 times 10 to the 23rd molecules of SO3. All right, so my moles and moles are canceling. Now I need to cancel out molecules. So what did I just determine with my picture? Right, 3 atoms of oxygen per 1 molecule of SO3. And I'm already to atoms. I'm done. I've met my goal. I've met my unknown. So my molecules of SO3 cancel here. And in my calculator, I need to type 1.14 times 6.022 times 10 to the 23rd times 3. Huh? Anybody have an answer? Okay, I'm going to do 2.05 times 10 to the 23rd. What? I got 23rd. Okay, majority wins. Okay. Oops, I just wrote 3 again. I'm going to try to see if I can check the math in my head, but I'll double check you guys and see it. Okay, but what's my unit though? Atoms of oxygen. So I can see that right here, atoms of oxygen. It's the last thing I didn't cancel out, or I could see it right here because I wrote down my unknown so I wouldn't forget what I was looking for. Are we okay so far? That was a hard one because you got to visualize what this looks like and understand what a molecule is versus a mole versus an atom. Okay, that's where the vocab comes in. Next, 4.52 times 10 to the -3rd moles of sodium phosphate to grams. All right, known is here. Question is grams of what? What am I looking for? Can you tell me that formula? We're just seeing S. PO4. There's one thing missing. Thank you. The 3. That phosphate is a PO4 3 minus, so it's a 3. And you crisscross it down. Sodium is a 1. You crisscross it down. It's there, kind of. All right. So I need to figure out how many grams of this I have. But before I can get to grams, what do you think I need to do? I know I can write down my known. I know I can do 4.52 times 10 to the -3 moles of sodium phosphate. But I need to get to grams, so what do I need to do? I need to account for the molar mass of that, because I can't do that work. I know I can put 1 mole down here, because moles and moles need to cancel. So 1 mole of sodium phosphate. But I need grams on top, right? I need grams of sodium phosphate at top. I don't know the number that goes right here, though. I need to calculate it first before I can actually finish my calculation out. So, back to the drawing board. Go for it. Sodium weighs, I have 3 sodiums, they weigh what? So 3 times 22.99 or 23, whichever one you choose to write, plus 1 phosphate, or phosphorus, which weighs 0.97 grams, and then 4 oxygens, which weigh each 4 times 16. Okay. So let me calculate that for me. 163.9 what? Grams per mole. Alright, so then that number is going over there. And you don't always have to show your work unless I ask for it. You can calculate that in your calculator. By all means, do it. In our 163.94 grams per mole. So moles and moles cancel. Left with grams, yay. Final answer? Make sure you put that negative in on the 3. Okay, it's 0.741 grams of sodium phosphate. 0.741. Alright, let's do a volume one. We haven't done a volume one yet. 2.5 times 10 to the second liters of carbon dioxide to atoms of oxygen. So we have known this, liters of carbon dioxide, and we have unknown atoms of O. So let's write out our known. 2.5 times 10 to the second liters, what's carbon dioxide? CO2. I need to be able to get to atoms. What's my stepping stone? Right. Anytime I have a gas, I can use 22.4 liters of, and that's equal to what though? 1 mole, right? So moles go on top or bottom here? Top. 1 mole of carbon dioxide is equal to 22.4 liters of carbon dioxide. Why did I put liters down here? So the liters of carbon dioxide cancel. All right. Now I'm in moles. I'm so close, I can taste it. All right, what's my next step? I can't go to atoms because this is not an atom. This is a molecule. What do you think we should do? You gotta go baby steps. You gotta say, okay, I have a mole of carbon dioxide molecules, and now I need to go to molecule. So go to 1 molecule of carbon dioxide, and then what do I need to do? Atoms of oxygen. Just like I did here, I had originally moles of SO3. And then I said, okay, here's my picture. 1 molecule has 3 atoms of O. So I need to get to molecule before I can even think about getting to atoms. So it's like you're breaking it down slowly to figure out exactly what you're looking for. So if I say 1 mole of carbon dioxide contains 6.022 times 10 to the 23rd molecules of CO2, that's gotten me down to what CO2 looks like, which is this guy. It's got me down to the molecule stage. Now I need to go one more. 1 second, I'm almost done with this one. Why did I put moles on the bottom? Cancel. So what's my next step? What? Right, so I need to do molecules on the bottom. So 1 molecule of CO2, and how many atoms of O? In this thing? 2. 2 atoms of O in that molecule. We okay with that one? Those are the harder ones because they're multi-steps. And that makes sense because now our molecules can cancel out and we're stuck with atoms. Yay, that's what we wanted. So when you calculate, make sure you put parentheses on everything. This times by 1 over 22.4 times Avogadro's number times 2 gives me 1.3 times 10 to the 20 times 10 to the 25th atoms of O. Question?
Where'd you get 22.4?
That was the molar volume. Look up the third conversion factor you wrote on the very first page of notes. So that was the molar volume I told you to circle. All right, last one. Formula units, because we haven't seen one of those yet. 1.91 times 10 to the 21 formula units of lead to iodide to gram. All right. So instead of writing formula units, let's write something that's a little more general there. What's a general name for one of these things? There were 3 of them. There were 3 different types. Representative particles. So instead of writing formula units, I'm just going to scratch that and just write it as a particle, because I think that'll ring a bell a little bit more than formula unit, right? All right, so if I start with my known here, and my question mark is grams of what? What's the formula? I used to set it. Give me the formula. PbI2, right? Because lead has a 2, that's what it tells me. Iodine has a 1 minus, crisscross down, that's what we're looking for. All right, so 1.91 times 10 to the 21, I'm just going to say particles. Particle, or you can put formula unit, either way, of lead to iodide. All right, I only have one option here. What do I have to do? Can I go from particles to grams? Straight. No, what's my stepping stone? particles to what? Moles. Thank you. Your mole is your biggest stepping stone. That is usually your gut instinct. You should always go to moles probably first. So particles to moles. What's the conversion factor? 1 mole over Avogadro's number, 23rd. I'm going to put formula unit or particle here. Either way, your answer will come out good. So particle formula units are gone, particle formula units are gone. I'm in moles of lead to iodide. What's my last step? Right, moles to grams, which is your molar mass, right? So I need to get moles gone, so I have to put them on the bottom. 1 mole of lead to iodide has a mass of, back to the drawing board. Lead, which weighs 207, I think. Double check. Okay, plus iodine. Don't tell me. 131? 126. Darn. Okay, 2 times 126. Whatever that is. I have that for you too. So plus 207. I got 461. Can I write that? Let's just do that. Because I got the number for you if it was 461. So we got 461.12 grams. So if I calculate this for you, this makes life better. So particles cancel, moles cancel. You're stuck with grams. Yay. Let's go. We are answer 1.46 grams of lead to iodide. You okay with putting all this in your calculator? I trust that you guys can do this. If not, you just have to practice some more. Alright, let's do one more thing here for you. After you write down what you need to write down. Yeah. Well, you're going to come into problems whenever you are trying to cancel something like here we get carbon dioxide and then carbon dioxide, and then I had to go to atoms. So if you don't write carbon dioxide there and you went to molecules, you might have said molecules of O and stopped. So it's going to become a problem when you have this types of problems where you're going from something to something totally different. If it's just the same substance the whole way, you never change the substance, that's cool. You don't have to write it. But that one I recommend you highly do. Okay. I got one more thing for you. These are your practice ones. We'll do that in a second. But who wants to go outside? Okay, so let me say the rules real fast because you need a break. Take a minute to absorb this, and I'll tell you what helps absorbing the sunlight, which contains UV, good X, what's in your radio, you know, all those wavelengths. Anyway, so I put some chalk on the lab stations. What you have to do is you have to find a partner. Hold on, not yet. So find a partner. You have to weigh your mass of your chalk. Who knows what chalk is made of? Calcium carbonate. Good job, Jillian. How did you know that? Oh, crap. Right, okay. Calcium carbonate. So you're going to go out, you're going to write your name, I love chemistry, Miss Emma's cool, whatever you want to write, on the sidewalk, nothing horrible, please. People will see this. Teachers will see this. So we're going to figure out how much calcium carbonate we used in grams, then you're going to convert it to moles and particles. Easy lab grade. Got it? So you have to mass first, so then when you go out there, you scratch it all up, and then come back here and mass it again. You don't really, you can write it, just a quick note on what it is, but all I need is the math and you and your partner's names, okay? So you have about 3 minutes to math. Now, I'll get out the door in 2.5 minutes. Let's talk now.